In this video, we'll be going over some logistic and exponential graphing and problems. So, let's start off with this question. In northern Alaska, the freshness of fish can be measured by its temperature, which can tell you how long ago the fish was caught. The temperature today is a balmy 27 degrees Fahrenheit. A large Alaskan salmon was caught by a fishing boat and its temperature was measured over the next several minutes. Use your calculator to find an exponential decay model to the data, making any transformations necessary for your calculator to run an exponential regression. So, now for this type of problem, we need to use Newton's law of cooling. And this basically is the expression temperature with the input of T is equal to T E of the environment plus T initial minus temperature of the environment times e to the power of negative kT. T, E, and V is the ambient temperature. Which here is going to be 27 degrees Fahrenheit. C initial is the initial. K has to be greater than 0. And this is also the cooling constant. And T is in minutes. So let's plug in what we have. So we have T of T minus 27 is going to be equal to T initial minus 27 times e to the power of negative kt. Now we can create a new variable of y is equal to t minus 27. So now the model becomes y is equal to a times e to the power of negative kt. And this is a pure exponential. Now we want to transform this for a calculator. And we can put this in the form of ln of y is equal to ln of a minus kt. So here, x is equal to t, and y is equal to ln t minus 27. Now we enter, in your calculator, you're going to enter the time values, and also this. So now you're gonna do regression. It's gonna be your third step. Now running regression will give you y is equal to, you're gonna use this and run the regression, and you're gonna get the function t of t minus is equal to 27 minus 57.9 times e to the negative 0.153t, and then this is your final model. And this matches the physical situation. As we know, it starts out cold, and then it increases, and then it approaches 27 degrees Fahrenheit asymptotically. So essentially that is the upper bound for what the y values will reach. So now let's do our next problem. Cicadas are emerging. When the temperature of the soil reaches 64 degrees, they emerge at an unconstrained rate of 15% a day. However, there are an unlimited number of cicadas in the ground. Scientists estimate that a total of 8 million cicadas would emerge from the ground. About 200,000 cicadas have already emerged starting May 20th, which was when the average soil temperature reached 64 degrees. Write an equation that shows how many cicadas emerged from May 20th. So this is a question about logistic growth. And what is logistic growth? Well, logistic growth, we can see this because the growth rate initially is exponential. So this is initially exponential, but we know that there is a limit because the population can only reach this cap. So that means that the growth slows as population increases. And logistics are a special type of exponential function. It's similar to an exponential function, but it's slightly different. So at first it looks like an exponential function, but then it curves off, and then there is this upper bound that it just reaches, and then it just never approaches. So it's like a S. So now the general logistic model is going to be P of t, and that's equal to L over 1 plus A times e to the power of negative kt. And here we know L is going to be 8 million. And then 1 plus A, E, and K is going to be equal to 0.15. And then we have T, and then we know that P initial, this is going to be equal to 200,000. So now we can write the model. So our model is going to be, again, 200,000 is equal to 8 million over 1 plus A. And 1 plus A, we can rewrite this whole entire expression to be 1 plus A is equal to 8 million over 200,000. And that's just equal to 40. So we get A is equal to 39. So now we can write our entire expression. Move this away a little. We can write our entire expression to be P of t is equal to 8 million divided by 1 plus 39 times e to the negative 0.15 t. And that's it for part A. Now for part B, we're asked, when do 6 million cicadas emerge? So that means we're going to set P of t equal to 6 million. And then you're going to solve for t. So you're going to have to perform operations on your calculator. You're going to invert this. You're going to have 1 plus 39 times e to the negative 0.15 t is equal to 8 over 6, because essentially all the zeros cancel out, and that's equal to 4 over 3. And then this is going to be equal to 39. You subtract 1 from both sides. So again, 39 times e times to the power of negative 0.15 t, and that's going to equal to 1 over 3. And then multiplying and getting rid of 39 on this side, then 39. Then you get e is going to be e to the power of negative 0.15 t is going to equal to 1 over 117. Okay, great. So kind of cramps. We have negative 0.15 t is equal to ln of 1 over 117. And we get this by taking ln of both sides. And when you take ln of e, that cancels out e. And that's how you get that. So then just computing this, we get t is equal to 31.8. After you compute this side, and then you divide both sides by 0.15 if you're confused how to get that. So that cancels out. So this is approximately 32 days that it takes for the cicadas to come out. So now let's do our last question. When does the effective growth rate fall below 10%? So the effective growth rate formula is for logistics growth rate. For logistics, this formula is going to be equal to, the rate is equal to k times 1 minus p over L. And we have to set it equal to 0.1. So plugging in everything that we have our k is equal to 0.15, 1 minus p over 8 million. That's our upper limit for what our population grow to. And then we set that equal to 0.1. So now we solve this. We have 1 minus p over 8 million. And then, okay, it's equal to 2 over 3. And then we get P is equal to 8 million over 3. Then now we solve this. Now we know that from earlier we had that P is equal to this expression, right? We have that P was equal to this expression. And we also know that P is equal to this, so we can set it equal to this. These are all equal to P, so we can basically set this equal, and then we solve for T again. So let's take this, then the answer that we got from part A, put that over there, and now you're just gonna solve for T. So you have 1 plus 39 times e to the negative 0.15t, and that's going to be equal to 3. And then after that, you have 39 times e to the negative 0.15t, and that's going to equal to 2. So that means t is going to be approximately 19.8. So basically, it's equal to like 20 days. Now let's do another question. Let's do question 4. So there's 1,850 students at TJ, and Model UN is trying to recruit all of them to join. And the club had 75 members last year, and this year it has 110. And if we model the size of Model UN using a logistic curve, how many years until 1,500 students are a member of this club? So we're given that the carrying capacity is gonna be L is equal to 1,850, and we also know that P of 0 is gonna equal to 75, and P of 1 is gonna equal to 110, because that was the year before, and then this is the year now. So these are our previous data points, and we use those when we're trying to predict further ones. So now we can model this with the relationship P of t is equal to 1,850 divided by 1 plus a times e to the negative kt. Now we want to find a, and we do this, we set P of t equal to 75, which is P of 0. Highlight this so that we can remember where that came from, and then you want to set it equal to the expression 1,850 1 plus a. And now from this we get a is approximately 23.67. So now we have to find k using P of 1 is equal to 110. So now we can do the same thing. We have 110 is equal to 1,850 divided by 1 plus 23.67 times e to the negative k. So then we get e to the negative k, after we simplify that expression, is approximately equal to 0.682. And then after this, we can take the ln of both sides. And then after we take the ln of both sides, that cancels, and we can flip that. And then we get k is approximately 0.383. So now we need to know, when will P equal 1,500? Which is what the question asks. When will we have 1,500 members in our club? So that means you set 1,500 equal to the function, and then you rewrite the model for it, and then you have 1850 over 1 plus 23.67 times e to the negative 0.383t. So when you solve this, and you get t is approximately 4.7. So that means about 5 more years until there are 1,500 members. So let's do another problem. Okay, so let's do this question about model and curve fitting. So a rectangle is inscribed in a circle of radius 2. Let let point xy be the point in the quadrant 1 that is the vertex of a rectangle is on the circle. Express the area A of the rectangle as a function of x and y, and use properties of circles to express the area A of the rectangle solely as a function of x. Okay, so for this you need the equation of a circle. So we have x squared plus y squared is equal to 2 squared is equal to 4. So we're gonna use to eliminate y. Okay, so what is the area of the rectangle? So the area of the rectangle is just going to be A is equal to width times height. So that's just going to equal to 2x times 2y. So that's going to equal to 4xy. Okay, great. So now we want to get, area in terms of x only. So then we know from the circle equation, we can rearrange this to y squared is equal to 4 minus x squared by just subtracting x squared. And then now that we have that, we know that since y has to be positive because it's in quadrant 1, as we know, it's in quadrant 1, right? So then we can write this as y is equal to the root of 4 minus x squared. So we know it's the positive one. So then we can substitute into, sub into a is equal to 4xy. So then we have a of x is equal to 4x times 4 minus x squared. So that's going to be your answer for that part. Okay. And what is the domain of this function a of x? So to find the domain, we have to look in the square root. Okay, so you have 4 minus x squared, and that has to be positive because anything under the root, it has to be positive. Otherwise, you don't want imaginary numbers. So we're complex. So solving this, we get this is negative x squared is greater than negative 4, and then just divide, and then we get x is in between these two values. So then we have to make sure that it's relevant to our problem. And we know that x has to be greater than 0, and that is in quadrant 1. So that means that the rectangle must have a positive width. So what that means is it's going to be 0 is less than or equal to x is less than or equal to 2. That's going to be the domain. Okay, so now graph a of x where the area is largest. So what we're going to do is, for this, we can just move down here. So we start at a of 0 is equal to 0, and we're going to end at a of 2 is equal to 0. And there's going to be one peak in between. So that means, therefore, we have one maximum guaranteed. So now we have to find the max. So the max occurs when the rectangle is a square. And we get this from the idea of symmetry. So that means we know that x is going to equal to y. So we can plug this into the circle equation. And then when we plug this into the circle equation, we get x squared plus x squared is equal to 4. So then this becomes 2x squared is equal to 4. And then we get x squared is equal to 2, so then we get x is equal to the root of 2. So now we have the max area, and that's going to be a is equal to 4xy. And now we know that what x and y are, so we get 4 times root 2, okay, root 2 times root 2. So then those roots cancel out, and then you just are left with one of them. That's going to be the square root of 4 times the square root of 4, and then that's just equal to 4 times 2, so that's just 8, and that's it. So we can start at like a of 0 here, and then we end at a of 2, and then there's one max in between. Now we want to find the perimeter next. So in order to find the perimeter, we know that P is equal to 2 times the width plus the height. So then P is going to equal to 2 times 2x plus 2y. And then P is going to equal to 4x plus 4y. Now we want to express it in terms of x. So in terms of x, it's going to be y is equal to 4 minus x squared. So then we get the function as P of x is equal to 4x plus 4 times 4 minus x squared. Now we want to find the domain of P of x. So the domain of this is going to be what was under the root, which is 4 minus x squared. It has to be greater than 0. So then we know that it's negative 2 is less than or equal to x is less than or equal to 2. So now the relevant domain, as we know, it has to be positive. So it has to be 0 is greater than x is greater than or equal to 2. So we have to add this constraint, because under the root cannot equal negative numbers. So now let's do this. Graph P of x for what values x is the largest. So we have to evaluate the endpoints. So that's going to be when P of 0 is equal to 4 times 0 plus 4 times 2, and that's going to be equal to 8. And P of 2 is going to equal to 4 times 2 plus 4 times 0, and that's going to equal to 8. Now the interior square, or the interior value, this is going to be the square. So this is going to be at x is equal to the root of 2. So that's going to be P is equal to 4 times the root of 2 plus 4 times the root of 2, which is equal to 8 times the root of 2, which is approximately 11.31. So the maximum perimeter occurs at x is equal to the root of 2. Now let's move on to our next question. So let's say that we have a rare species of insects that were discovered, and in order to protect them, environmentalists declare okay, this is not loading. Actually, let's okay, sorry. Yeah. Okay, a rare species of insects were discovered, and in order to protect them, environmentalists declare the species endangered and transplant the insects into a protected area. The population of the insect at T months after being transplanted is given by P of T is equal to 50 times 1 plus 0.5 times T divided by 2 plus 0.01 times T. So first, how many insects were discovered? So this means that we need to look at the initial population. So we have to look at T of 0. So then when we sub in T of 0, we get P of 0 is equal to 50 times 1 plus 0 divided by 2 plus 0. So then we get 50 over 2, and then we get that's equal to 25 insects. Now, what will the population be after 5 years? So how many months is this? So that's just 5 times 12. So that's equal to 60 months, okay? So now we have to sub in t is equal to 60. So now we have p of 60 is equal to 50 times 1 plus 0.5 times 60. And then that's divided by 2 plus 0.01 times 60. Now we can simplify the numerator, and then we get this is equal to 1 plus 30 is equal to 31. And then that's going to be equal to 50 times 31. Put that up there. It's a little. And then we have below, we have 2 plus 0.6 is equal to 2.6. And now dividing this, we get 1,550 over 2.6 is approximately equal to 596 insects after 5 years. So now what is the horizontal asymptote and the carrying capacity? So now we have to identify, we have to look at leading terms. So what does this mean? So we have to look as t approaches infinity. The numerator is going to behave like 50 times 0.5 times t, which is going to be 25 times t. And then the denominator is going to behave like 0.01 t, because these are the largest terms. So then you take the ratio of this. So it's going to be the limit as t approaches infinity of p of t. That's going to equal to 25 times t divided by 0.01 t, which is equal to 25 times 0.01, which is equal to 2,500. So the horizontal asymptote is going to be y is equal to 2,500. So this is the max sustainable population of the protected area. So now let's move on to our next question. UPS has contracted you to design a closed box with a square base that has a volume of 10,000 cubic inches. They would like for you to minimize the cost of the supplies to make the box. Find the function for the surface area of the box and find the minimum amount of cardboard that can be used to construct the box. What are the dimensions of the box? So now we want to start with this. So we know that the volume is 10,000 inches, and we know that this is a square box with a closed box, and we want a square base with a closed box. That is a closed box, and we want to minimize the surface area. So we want to define our variables first. Like x is going to be the side length of the square base, and then h is going to be equal to the height, and we know that we're going to try to create a representation for the volume. So the box is specifically going to be v is equal to x squared times h. So that gives us x squared is times h is equal to 10,000. And now we solve for h. H is going to equal to 10,000 over x squared. And now we want to write out the surface area. So surface area is going to be, we know the top is x squared, and we know the bottom is going to be x squared, and then we know that the four sides will be 4 times x times h. So s is going to equal to 2x squared plus 4x times h. Now we want to sub in h. So subbing in h, we take this expression, and when we sub in there, so then we get s of x is equal to 2x squared plus 4x times 10,000 divided by x squared. So then we get s of x is equal to 2x squared plus 40,000 over x. So this is going to be the surface area function. So now let's move on to our next part. Okay. We also want to minimize surface area. So in order to minimize surface area, we have to take the derivative, which is s prime of x is equal to 4x minus 40,000 divided by x squared. And now we want to set this equal to 0. So then we can, after we set it equal to 0, we just add 40,000 divided by x squared to both sides, and we get 40x is equal to 40,000 divided by x squared. And now you multiply both sides by x squared. And then you would just get x to the 3 is equal to 10,000. And then x is just going to equal to 10. So now we want to find the height. So h is going to equal to 10,000 divided by 10 squared. And then this is just going to equal to 10,000 divided by 100. So now we get h is equal to 10. Now we want to find the minimum surface area. So that means we have s of 10 is equal to 2 times 10 squared plus 40,000 divided by 10. That's going to equal to 200 plus 4,000, and that's going to equal to 4,200. So now we are done with this part. So now let's say we have some true or false questions that we can answer. So we know that, okay, the factors of the denominator of a rational expression are used to decompose into partial fractions. This is true because partial fraction decomp it's based on the factoring of the denominator. The graph of a polynomial function sometimes has a hole. This is false because polynomial functions are continuous everywhere. And holes they can only occur in rational functions because of the division and the constraints of making the denominator not equal to 0. So yeah, and now the graph of a rational function, okay, sometimes it has a hole. Yeah, the hole happens when you can cancel a factor in the numerator and the denominator. So there's a common factor. The line y is equal to 1 is a vertical asymptote of x to the x cubed minus 1 divided by x cubed plus 1. And this is wrong because this is a horizontal line because the height will always be 1. And the vertical asymptotes are when the denominator is equal to 0. So we have f of x is equal to 3 divided by x minus 2 and is continuous everywhere. So this was false. This is false as well because it's undefined at x equals 2, and that's not everywhere, so that's false. So now it's ln 10 minus ln 5 minus 1 over 3 times ln 8 is equal to 1. This is false. This is because we can write this over here. ln 10 minus ln 5 is equal to ln 2. So then we have 1 over 3 ln 8 is equal to ln 2. Then we get ln 2 minus ln 2, which equals to 0, and that does not equal to 1, so that's false. The graph of y equals ln x is an increasing function. That's true because ln x is kind of like wait. I might have it reversed. Yeah, it's like this. I don't know what I was doing. Okay, yeah, it's increasing for all x is positive, okay? So now we have MCQ. The rational function f of x is equal to this. Now from this, we can cancel out x minus 1, so you're just left with this.